To light or not to light, that is the question. William Crookes was a chemist and a physicist, born in London in 1832. He started to study, in 1903, the phenomenon of radioactivity. But for now, let's put radioactivity aside and let's have a closer look on Crookes' radiometer. His radiometer is made out of a partially empty inert glass bulb, containing a vertical metallic axis, and on the axis there are 4 rotating square vanes made out of mica. Let me show you my radiometer. Here, as the window is closed and doesn't let sunlight in, the radiometer doesn't turn. On the other hand, here, the radiometer turns as the open window lets sunlight in. Here, we will use a filament LED bulb to see if the radiometer turns. Let's turn this light on. We can see the radiometer turn, but very slowly. Now let's use a 60-watt incandescent bulb to see the effects on our radiometer. We turn it on. As you can see, it makes the radiometer turn. And it turns very fast after all. Quicker and still quicker. With the radiometer, we discovered that these bulbs with equivalent luminosity make the vanes turn at different speeds. So clearly something is going on that we cannot see even with our own eyes. Now let's thank Mr. Crookes and his radiometer for this interesting discovery. And let's move on to the next big question. What is the difference between these two sources of light? Let's not leave this question without any answer. And let's study these sources through a prism. A prism? Wait, prisms aren't precise enough. So let's benefit from today's technology and let's move on to the spectrometer, a device which replaces the prism. Spectrometers are devices that capture light sources through fiber optics to break down light and display the corresponding spectrogram on a computer. As you probably know, radio waves span a whole spectrum from gamma rays that are dangerous all the way to radio waves that carry music and news. Here we will focus on the visible light range from 400 to 700 nanometers. Let's use the spectrometer against the 2 different light sources we used on the radiometer. We start with the incandescent light bulb. Let's zoom on the spectrogram of the specific light source to show the distribution of waves along the visible spectrum. Next, we analyze the filament LED bulb with the spectrometer. Here again is the fiber optic. Let's now turn on the light. Let's now see if this spectrogram is different from the previous one. Oh yes, it's clearly different. Let's compare side by side. Do you remember which is which? Here you go. Let's take a closer look at the left one. The incandescent light spectrogram peaks around the yellow wavelength but is widely distributed across the entire spectrum, from UV lights to infrared. Let's overlay the LED light spectrogram. As you can see, the shape of the gray spectrogram is very narrow with higher intensity around the yellow wavelength, and a sharp drop near the red. On the other hand, the incandescent light shows activity near the red and infrared, which is where heat comes from. We finally have some idea about the invisible differences between these two sources of light. Modern lights are 7 times more energy efficient for the same intensity of light. They also produce much less heat than the incandescent bulb. They can help save $140 billion of electricity per year. So if you haven't done it already, switch to modern lights. Thank you for watching my video. I hope you enjoyed it. If you learned something new today, don't forget to drop a like down below and share it with your friends.